elastic, and inelastic. These formulas, the code had already used it to compute this value. There are a whole bunch of tables that they use this formula to compute the value. So we sometimes we go directly to the table and find the value. But in this new code, I don't know if you can read in your code, this is L to C over R. Well, this is in reality, this is KL over R. So this is a different way. L to C is a KL now. So, but in the old time, in mechanical solids and everything, it's called KL over R. So what determines which formula you have to use, inelastic or elastic, is this value. When this value is small, I'm going to tell you why this formula controls. When this value is large, this formula. And this value in here, if you can read in your code, is F sub E. So this, I don't know, you call, my code is 16135. I don't know that you had a different, Christian, I don't know, you have a different code. Are you sure the 16535? Should be 16135. Anyway, so this little value, F to E, is the Euler formula. And it's given on the next page. On page 16.136. 16.136. This is the Euler formula written in a different way. And this is what you learn in mechanical solids. So I'm pretty sure that you don't remember the Euler formula from mechanical solids. So this is what we're going to use. In addition, in chapter B, on page 16.117, go to chapter B, 16.117. We're going to use this table. We're going to use this table to check what is called local backlink. Because the columns, we're going to be checking a lateral backlink and local backlink. This local backlink is for the flanges and the web. And it gives you the width to thickness ratio. And this is for compression. You have to be careful because the next page is for bending. And compression elements for bending is very simple to understand because whenever we had a beam, the bottom is working under tension, the top is called the compression flange. So this you have to be careful. This is for the next chapter. Here we're going to go and look at only this table. Compression element for axial compression. But this is a very interesting table. If you look at this side of the table, and a stiffened element, and the other one, it says stiffen element. And stiffen are the flanges, stiffens are the web. And there is a line in here for the flanges, case 1, 2, 3, or 4. For the web, 5, 6, 7, 8, or 9. So this table, for instance, if you look at the case here on the top, for this is a hot roll because they also have for built up. But here we had a hot roll. Look, P over T with a to thickness ratio, the B over T, you're gonna see that this is the width of the flange divided by 2. So if you look at this little b in here, it means the flange divided by 2. So this is going to be b over 2 times the thickness of the flange. But whenever we had a channel, it's the entire width of the channel. So you do have to be careful what the little b means. And we're going to be using also case 5, H over TW. And H is indicated in here. So this, we're going to use it to check local bucket. So this is a table that you need to be able to use. Appendix 7 on page, go to page 16.1570. And this is the page. I will go about Stephen a little while. I'll go back. So 16.1570, the K value that we have to use to determine what they call the effective length. And this is also from mechanical solid, probably you don't remember for the corner. For instance, what is fixed and fixed, this is what we learned in mechanical solid 0.5. But for the American Institute of Steel Construction, for our course, if we had a fixed, we're going to use this value here that is 0.65. If we had a fix and a pin in theory 0.7, we're going to use this value of 0.8. One of the most common one is this. Pin, K is going to be equal to 1. Whenever we have frames, on the next page, 16.1571, whenever you have a frame that there is no lateral movement, a brace frame with there's no size with no lateral movement, you can see a brace frame in here that the joint they do not translate. There's no delta. So the way you find the K, look, K go from 0.5 to 1, never larger than 1 for a brace frame. And you can see in here we had a column, girder. We're not going to use it this semester, but just in case you compute GA and GB, whenever those values, the GA and GB, whenever they intersect, you find the value of K. We're not going to use it, but good to know. And on the top of the next page, page 16.1572, it gives you how to compute G top and G bottom. And it's based on the stiffness of the column over the stiffness, summation of all the stiffness of the column, framing into the joint over the stiffness of the girder. So we find GA and GB, G top and G bottom. what I want you to know below. This is a frame that is not braced. This is a frame that is not braced. So when GA and G top, you can see that there's a delta. Look at the delta. This is the size way. It's typical a moment frame. So for this frame, all the connections are moment connections. For the previous one, all the connections are shear connection, but you have to put an X brace. So whenever we had a moment frame, look, the value K go from 1 all the way to infinite. And again, you find G top, G bottom, whenever intersect, you find that value. Before I go to chapter 4, there is a question. I'm going to give you. The question was about stiffen and stiffen. Whenever you apply a compressive load, there are going to be compressive stresses all over. So these flanges, they're going to, based on the stress, they're going to try to back up. Nothing is supporting this frame. These flanges are free. You can see nothing is supporting this flange. Nothing is supporting flange. But the web, this web is like a little column supported by this flange, this flange. So they call the web stiffen because it's supported by this flange and this. They call the flanges and stiffen. So whenever we have backling, this flange could do this. It could do, let's say, this. Because nothing is supporting the flanges. That's why they go and stiffen. But in comparison, if the web is going to buckle, it's going to buckle something like this because it's supported here by the top and the bottom flange. So that's the difference between a stiffen and a stiff. Any other question? Okay. Sometimes I miss your questions, so I will look back, see if I miss something. So now we're going to go to chapter 4. I'll tell you the page. This is chapter 4, page 4-1. Okay. Look, in this chapter, we had everything that we ever wanted. I'm going to show you different values. Go to page, for instance, 4-25. All of this table, go to chapter 4, page 25. So the formula that I told you, in chapter E, formula for elastic or inelastic buckling, they have used those formulas. If you look at I'm on page chapter 4, page 25. Just to give you an example, but all of those tables are very, very similar. So this is chapter 4, page 25. Whenever you go to this, you're going to find L to C with respect to the least radius of gyration. So this is KL. KL, L to C is KL in feet, not in inches. And with respect to the y-axis, because whenever we had a y flange, the largest moment inertia is about this axis. So this is what we call the strong axis. So this is the strong axis. And this is the weak axis. So if we do not have any braces, a Y flange is always going to buckle about the y-axis. That's why this table, and I'm back on page 425. I'm back on chapter 4, page 25, but all of those pages are similar. What I want to say is that all of these tables are for weak axis control. So all of these tables assume that it's going to buckle about the weak axis, that is the y. That's why R sub y. But there are certain cases that we put braces and the strong axis will control. I'm gonna work some example with strong axis control. But if there are no braces, I'm gonna tell what braces mean. It will buckle about the y-axis because that's the weak axis. So we're gonna use these tables to do our design. I want you to go to the end of this chapter, to the end, to page 4-229. Chapter 4, page 229. Chapter 4, page 229. And this is the beginning of the table where for FY 35, 36, 46, 50, 65, and 70, you're going to find the critical stress based on this value in here, L to C over R, is the KL over R that I told you before. With the largest KL over R, you're gonna go to this table and you're gonna find the value of your critical stress. And it goes from 1 all the way. What is the maximum value of the KL over R that you can have? If you look at this table on the left, what is the, no, keep going all the way to the last page. Go to page 4-233. 200. Because the code says the same that we did when we're doing the tension design, we had L over R. Whenever we do tension, L over R had to be, what was the value that we couldn't exceed for L over R for whenever we were doing tension design? And for tension design, it was recommended. But for compression, it cannot exceed 200. So KL over R has to be smaller or equal to 200, never larger than 200. That's why this table goes all the way to 200. Now I want you to go from page 4-233, go like the Chinese people go to the previous, and I want you to find me for the value of KL over R when all the values are the same. Doesn't depend on 35, 36, 46, 50, 65. See if you can find me when at what value K over R, the values don't change. They are the same for no matter what type of steel. So, for instance, if you look what I'm saying, you look at page 233 or 161, look, if you look at this page, all of these values are exactly the same. All of these values are exactly the same. Tell me, where is the limit when they're no longer the same? What can of our value? What value? One 33 is not correct. 134. Is 134 the winner? Anyway, so I just want you to be aware that after you get to certain value, it doesn't matter. It doesn't matter what type of steel, all the values are going to be the same. This is the second page. This is the second page that talks about con. I'm going to get something. Look, I'm not with you, but if I were with you, I have my stick and I would pretend that the stick is a column, eh? And I will apply a load. And when I apply a load, this is going to bend. Look, apply a load, this is going to bend. So if this is a look at the cross section, it's a rectangular cross section. And this is a column. If I apply a load, this is a column, the same as if this were a column, and we apply a load. Since this has a rectangular cross section, this is going to bend. If we call the strong axis is the horizontal, the weak axis is the vertical. If I apply a load at the top, which way do you think that it's going to back or bend? You're going to do about the y-axis or about the x-axis? You're going to come this way or you're going to go that way? Which way do you think? You're going to go about the weak axis, the y-axis. So sometimes we put a brace in between. So it will not backward about the weak axis. So what I have in here is a typical column. And I'm going to put it this way so you can see that is a column. So it's going to bend whenever we apply an axial load, and the load has to be applied at the centroid. It's going to, if there's no brace, if there's no support, is no support in between, if nothing is supporting the weak axis, it will bend about the weak axis. And so we say that it's a stability it will fail because of the stability, and we call it lateral buckling. So whenever we had a situation like this, in mechanical solid, when you took mechanical solids, and I'm pretty sure that you already forgot it, but this in here on the top, this is the Euler or Euler formula. This is the critical load. The critical load is pi squared E times the gross area of the K over R squared. But this is normally what we show you. This is the way we show it to you in mechanical solid. The critical load pi squared EI over L squared. And later, because the value of I, as you know, the radius of gyration is equal to the square root of I over the gross area. So normally we say R squared is I over the gross area. And we replace I by R squared times the gross area. So this is the Euler formula that supposedly you have seen in mechanical solid. This formula is given in chapter E. This formula is used everywhere, the Euler formula that is called the critical load. If I were in front of you and I asked you, have you seen before? You would say never. We didn't cover that. And probably you're right, but I don't know. The only thing I want you to know is that in mechanical solids, we teach about the critical column, the critical load is called the Euler load. That's the only thing that you have to know. And that's a very, very old formula because those centuries ago, the Euler was able to determine that. And on this axis, in this figure, on this axis, is the critical low. And here, this is what we call at the bottom, if you can see, this is the most important value that we use for column. That is called slenderness ratio, how slender the column is, the KL over R. And if you look at this dotted line, after I continue in here, that's the Euler formula. This in here, and all of this, the results of tests in the lab. If you took mechanical solid last semester, you were fortunate you tested some column made out of wood, I assume. If you take the materials lab this semester, you're testing nothing. You're probably gonna see a video. But believe me, whenever they do this in the lab, now we know something that we didn't know before. That look, this Euler formula, it predicts very good values from here, from this value to the right. Euler is great because all the results of testing, all these results fall below this formula. But from here to the left, look, Euler is telling you that you have more load than in reality you have. It's telling you have more capacity for more values, okay, over R. This formula doesn't work. Different doesn't work for more values because that means it's not very tall column. This failed. It's telling you that you have more capacity than you do in red. It's dangerous, no factor safety. That's the reason why the code has two formulas. Elastic formula from here to the right. Inelastic from here to the left. Why? Because now we do know that whenever we had a small value of K over R, whenever you have applied a compressive force, portion of the cross section has already yielded. Portion of the cross section is inelastic. Portion of the column cross section already got into Fy or past Fy. And if you look at this value of E, that I put a circle, this is the elastic modular elasticity. Whenever you go to an area that you are no longer in the linear portion, that value doesn't work. And this is the problem that we had with Euler, that it gave us the wrong value for small values of KL over R. I want to show you on the next page, on page 4. This is a typical stress strain diagram that we find in all the textbooks we did before we learn about yielding and rupture. We look at this, and there is a elastic, there is a plastic strain hardening. So for small values of KL over R, portion of the cross section has reached this value. For large values of K over R, it's always elastic. You can see that the slope of this line is the modular elasticity. In here, we don't have this value of modular elasticity different. In here, they use a tangential value for the modular elasticity. It changes. That's the reason why this formula was failing, because we had inelastic and elastic. The code has already taken that into consideration. That's why we had two values, two equations, one for inelastic, one for elastic. This is page number 5. And in page number 5, this is the same that the code has, just without any information. Now that we have information, we know that these are the theoretical values that the code recommends all the values. But look, and here's always pin K1. In here, the code sometimes recommends different values, but this is from this point to this point, that is the KL. From this point to this point, the KL. Look, they have two values. We use always the largest. If you look at this sketch, this is more than that, always the large. And this is what we were saying before, whenever they join, doesn't translate. This is a brace, typical steel frame. This is the value of K. This is going to be a typical case that we're going to be looking at later. Only whenever we have column, only axial load, we do not have a moment. At the end of the semester, we're going to be looking at beam columns that will have axial force and a moment. So whenever we have this, we know the type of steel, the type of support. We're going to find out what is the design strength. So what is the phi p sub n value? Phi p sub n has to be larger equal than pu. Pu is the required value. This is a similar case than the one before, that is fixed and pinned. And if you look at this different view, if you look at what we had in here, you see this dotted line? That is the web. And this is the flange. So we're looking at this shape. We're looking at this. So this is buckling about the weak axis. You can see the column here buckling about the weak axis. In here, look, these are the flanges. The flange, and here the web and web. So look, this is buckling about the strong axis. The only time that could happen is if we brace, if we brace this could control. This could give you a larger value of KL over R if we are bracing this. The tables are for weak axis control, but sometimes a strong axis control, so we have to do something else. But for the tables, they always assume that the weak axis. If you were wondering what I'm talking about bracing, this is a typical case. I want you to look at this very carefully. And don't forget that I already uploaded my notes. And if by any reason you don't have access to Blackboard or you need me to email you my notes, I will do it. But I want you to look at this. Look, it's a brace frame, so this, the top and the bottom, they're gonna move. Now we're supporting the weak axis. And on this view, you can see that we are bracing the weak axis with a wide flange beam. It could be a channel, it could be any, but we are giving lateral support. So this web is supported in here. So now instead of doing what it was doing before, this is the way it is going to backle. 14 and 14. But the strong axis doesn't have that support. The strong axis still backle this way. So for the weak axis, the KLY is 14. For the strong axis, the KLY is 28. If we do KL over R for 28 and KL over R for 20, for 14, this might control. That means that for the strong axis, you could be here. For the weak axis, you could be in here. And the one that control is the largest value because give us a smaller critical stress. So there are several problems that we're gonna look that they had this situation where we bracing the weak axis. I'm gonna jump to page 10. This is what we do for local backlink. This is what I did show you in chapter B. And for projecting plan that is, look, and Stephen, the B over T become BF over 2 times the thickness of the flange, and we have to compare with this value. And here you see a Stephen, and they give you H over TW, and we have to compare with that value. Otherwise, we're going to have local back. The code has already computed the value of B over 2 times the thickness of the flange and H over TW for you. So you don't have to compute it. I want you to go I want you to go to page 1-23, one example. Chapter 1, page 23. So you go to this page, and for instance, I want you to go to the very top value, in here. Look, they call compact section. Look, B over 2 times the thickness of the flange, H over 2 W. For this section, already being computed. For every single section is already being computed. go all the way to the left to the next page and tell me what section it is. It's W what by 311. What section is this? W what by 311? W18 by 311, exactly. So every section on the right side, it had this information, so we don't have to compute it. It's already given for you. Most of the standard section, most of the section given in the code, they do not have local backlink of the web. Some of them, very few, have local backlink of the flanges. And if there is a local backlink of the flange, if there is for compression, they will put a little C next to the section. For bending, they will put a little F next to the section. I want to show you. On page 1-26, chapter 126. Go to chapter 1, page 26. In chapter 1, page 26, at the bottom of the page, you look at section W12 by 16. W12 by 16, this section. What letter do you see in there? See, and in the bottom, we say that this is a slender. That means local backlink. And the one on the bottom, it had a C and a little V. So that also had problem for compression and also problem whenever you had a shear stress. So the code has done that job for us. But I want you to know, as a good practice, no matter what the code has done for us, I always want you to check for local backlink. I'm going to repeat that later because some of you already left, but always it's a good practice to check for local backlink. And this is what the code has. That's why for a wide flange, is B over 2 times the thickness of the web because they use 50% of the web, 50% of the web. For a T, this is the D. So everything that we had in here deal with local backlink. The same whenever we had, I mentioned for a channel, this is the value of B. For a double angle, in here, this is the value of B. And look, there is a separation. In here, no separation, back to back, that's the value. Something that I mentioned in class a long time ago, that all of these sections are hot roll. So all of this section, I gave you a picture how they are fabricated at the mill. They start with a chunk of steel, real hot, they roll it. So as a result, uneven cooling because these flanges that are exposed to the air more than this intersection. So these flanges are exposed to the air more than the intersection. This is exposed to the air more than that. So as a result of uneven cooling, there are residual stresses in the cross-section that we don't see them. And sometimes the compression is as high as 12 KSI. So if you apply more compression, it increases your stress and you don't know. If it's tension, it decreases. But all of this, the code has already taken into consideration. The only thing that I want you to know is that there are residual stresses. We do not have worry, because all of the formulas in the code, they have written by the Structure Stability Research Council. All of the formulas take this into consideration. Whenever we have built up a wide flange by welding, because of the welding and cooling, we creating also stresses. Look, group welds, so there are also residual stresses whenever we have built that section, but the code already taking that into consideration. I'm going to start with one problem. But I'm not going to finish this problem today because we've done a lot. And I know it's very difficult online. I understand how you're feeling. I'm feeling the same way. But this is just an example that I'm going to do it tomorrow. Fy is equal to 50. We always want the lightest shape. The lightest shape is the smallest weight per foot. The dead load 200, the live load 200, and they want you to find the lightest section. And you have to consider W8, W10, W12, and W14. And the same that I showed you before, there is a brace, a weak axis is brace. So we had, instead of 18, we had 9 and 9. Here, 9 and 9. And for the strong axis, we had the total, the 18. And we need to find the lightest section. So to find the lightest section, we're going to go to the code. For instance, I want to go to page 4-24. Page 4-24. Whenever you use the code, you have to be very careful because there are too many tables. Look, this table is for 50 KSI. In the next page, we have for 65. And in other pages, they have for 70. Look, 70 KSI. So you have to be very careful whenever you use the code. Always check that you're using the correct table. So don't forget. Always look for the correct table. Always check the Fy equal to 50. All of these tables, they have used the equations in chapter 8 in elastic and elastic to compute this value. And in this table, you have to go with a weak axis. All of these are for weak axis. Even if strong axis control, you always have to go with, you start with a weak axis, but most of the time, weak axis control. But this table, if you look at what I have in here, W8, this table is for W8. I'm gonna go to the previous page and follow me. What size do you see now? W what? What size you see? W10. And look, when they finish with the W10 and the way it's organized, 39, 45, from lighter to heavier. I'm gonna go to the previous page, follow me. What sizes do you see? 12. And again, organized from lighter to heavy. And let's go until we find a heavier one. What size do you see? 14. And if we keep moving, do you find anything larger than 14? No. They had that because those are the most common ones. W8, W10, W12, W14. So whenever we're going to solve a problem, we are going to look W8, W10, W12, W14. The one that is the lightest one, the one that has the least weight, that's the one that we're going to check. And if it doesn't work, we're going to go to the next one. But if you look at the code, in the code we have, for instance, the section, I'm going to give you a W21. So if somebody asks you for the W21 that is not on this table, the only thing that you need to do, you go to the where the W21 are, you close your eyes and select any section. So if they give you a section that is not W8, W10, W12, 14, you just go to chapter 1, close your eyes, and select, for instance, W21 by whatever. Why? Because once you go to chapter 1, you had all the properties of the geometry. You had the gross area, moment inertia, everything, especially Ry and Rx. Because what you do, now you have KL over Ry. With that, you find the critical stress. I'm going to show that to you. But this is what we're going to do. And so for tomorrow, I have prepared a table for this problem. I have prepared a table. And if you can make a copy of this table for tomorrow, it will be useful, very useful, because that way we can fill it out together. I have already done it. You look at the next page, I already done it for you. But it would be a good exercise if we at least we can do one together. So for tomorrow, if you cannot print, just copy by hand. But we're gonna go over this table. And I'm also going to show you where the values are coming from. I'm going to stop in here and to see if anybody, now you can turn your camera and you can turn everything on. If anybody has questions or anything that you want to know, anything that um, you need me to clarify, remember it is very difficult. Okay. It's very difficult online and you can.
Thank you very much, Dr. Araya.
Right. All right. Well, remember my office hours are Monday and Wednesday from 1 to 3. Too much interview.
Professor, I have a question about method connections.
Yeah.
Is there like a
Wait.
step-by-step
Who's that? Hey, I tell you what. Write the question. Right. Yeah. Just turn your mic. Turn your mic off. You can keep the video. So let's review it. Okay. So write the question.
I'm typing the question out.
I cannot see the question.
What is?
Okay, I don't see. What's the question? Type the question. Oh, wait, sorry. I need to put this back. Just a minute. Just a minute. Put the chat back. Okay. Is there a step by step you could outline for someone program using well the connection? Well, um, the um, the only thing that I've done step by step right now is the eccentric welder connection. But I'm going to prepare a example to tell you what in general you should be doing. And being online, it is more difficult to communicate. So I try to put as much information as I can, like I had done for Eccentric World Connection. And I try to see, but any problem in engineering in general, they're open-ended problem that you have the information given to you, and based on information, you say, okay, of course, if they give me the service low, I need to compute uh, what is the factor load. And also remember now it could be tension, it could be eccentric shear. Now we have compression. So you have to understand what type of problem they're asking me. Because sometimes I'm giving a problem that the connection is not eccentric. And the way you looking at the connection to you appears to be eccentric. So you go and solve a problem that is completely different and impose your problem. So something you have to be is observing what kind of question I have in front of me. The compression, tension, eccentric shear. So that's it. And after that, you already had a tool, where you had to compute, like we did in tension, that we had tension yielding, tension rupture. We had the bolts. Now we don't have the bolts anymore. We had the block shear. We do have the block shear, but we didn't before we have bearing. Now, what we had to do for well, we had to check if the capacity of the well is controlling or the shear yielding or the shear rupture. Hey, don't forget that somebody need to send me the video yesterday, because I don't have the recording. This week I'm gonna be better prepared and changing the system. Any other question?
Thank you, Professor.
That's it? Okay, I think it's enough torture for you and for me. So I'm going to stop here. I'll see you tomorrow. Be on time, please, because I know that every time that somebody comes in, it makes noise. All right. Hey, goodbye, everybody. Have a wonderful day. Hope to see
Adios.
you sometime in person.